Hey, welcome back to physics. Today what we're going to do is go over the uniform circular motion. Okay, uniform circular motion. Now, one of the questions we want to ask ourselves is how? How can an object travel in a circular path? Okay, how can it travel in a circular path? Now, the reason why we ask that question is because what we just learned a few lessons ago is that Newton's first law of motion here states that, of course, if, let me cover up part of this here, an object at rest stays at rest, and an object in motion stays in motion with the same speed. In other words, the velocity doesn't change, and in the same direction unless acted upon by an unbalanced force. So in other words, for an example here, if we had a baseball and Newton's law of motion completely holds true, then when you throw that baseball, if you neglect air friction, that ball should continue on at a constant velocity in a perfectly straight line forever and ever and ever. Okay? But reality tells us that it's not going to do that, is it? No, instead the ball is going to drop off and start curving downward. Okay? Now, the question is, why? Right? That's the question we're trying to answer here is how? How and why can an object travel in a circular path? Well, according to Newton's law, that's supposed to travel in a straight line right there. But there must be some other force pulling on that ball. And of course, you all know from all the stuff we've been studying about kinematics and everything, what's the one force pulling down on that ball? And that is gravity. There's the force of weight, is what we like to call it, m times g. We have that force of gravity pulling down on that ball. So in other words, it is obeying Newton's first law. It is supposed to travel in a straight line, but that unbalanced or that net force acting on it is going to be our force of weight. That's what's going to create a curved path. So that's what answers that first part of the question. How can an object travel in a circular path? Well, it has to have some sort of outside net force pulling on it. It creates that curved path to it. Okay? Now, there's a way of taking that and going even a step farther with it. And Sir Isaac Newton did that with something called the way I saw it in a book. They described it as Newton's thought experiment. Okay? In Newton's thought experiment, his idea is that you would take a really large cannon right here. You put it on top of the highest mountain we have on our planet. And of course, we're going to take a whole bunch of half dozen cannonballs and some gunpowder, and all the cannonballs have the exact same mass and size. And we pack in a little bit of gunpowder in that cannon. We put in our first cannonball, light the fuse, boom. The cannonball comes out, and just like the baseball, it curves, comes out, and gravity pulls it down, and it curves down and hits the surface of the planet. Now, the second shot we're going to do is we're going to pack in a little bit more gunpowder. We're going to give that cannonball a little bit more velocity coming out of that muzzle. So now what we're going to do is the cannonball still has to fall, but when it comes out faster. So of course it's going to go a little bit farther. It's going to have a little bit farther range. And of course gravity begins to pull on it, pulls it, pulls it, pulls it, pulls it, pulls it, pulls it. And here we have the path for part B right here. That dotted line right there comes down. So the cannonball comes down a little bit farther. Now the next idea is that you're going to put the same kind of cannonball back in, but this time we're going to pack a lot of gunpowder in that thing. We're going to give this cannonball a lot of velocity. So we shoot that cannonball out. It comes out, and there it is. Gravity's pulling on it, so it's got that curved path right there. That's that dashed line right there. So that curved path right there, gravity is pulling on it. But what's so unique about it is, remember, the surface of our planet is not perfectly flat. When you look out the window and you look at your backyard, you look around, a lot of different areas have just got a flat, so we tend to think of everything as flat. But of course, the surface of our planet is curved. So when that curvature, that trajectory right there comes out, and it matches the curvature of the planet, well, that means as this cannonball is actually curving down the fall, the curvature of the planet is curving away from the ball. So it goes all the way around the same way, all the way around, round, 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 round. And Sir Isaac Newton theorized that if you shot the cannonball out with enough velocity, that the curvature of that trajectory should match the curvature of the Earth. means that cannonball will come right back and boom, hit right in the back of the cannon. That's the basic first initial idea of putting something in orbit. Now the next idea is to take and put a lot more gunpowder into that thing. And as you put more gunpowder into it, the ball goes out and it's got the curvature is even less, has less curvature than the planet does, which means it takes it to an outer orbit, takes it further out. And of course, the other idea, the last idea, is to put enough gunpowder in there that you get to shoot the cannonball or projectile out so that your object comes flying out of here and actually escapes, which is known as your escape velocity. Okay? So that's the general idea of that curvature motion. We have to have that force acting on this, a net force pulling on that object to make it curve down to create this circular motion. Okay? Now, there are different things that are going to cause that net force. Okay, in this example, in the baseball example we just saw, it's the force of gravity. The Earth pulling this force of gravity, that's what's going to provide the force to pull this on around. I want to show you another example. Let me move my papers around here real quick. And that is a car going around a curve. Okay? When we have a car going around a curve, we got the bird's eye view here. We have a car going around the curve. Now, according to Newton's first law of motion, this car is going to want to travel in a straight line, just like that, at a nice constant velocity. This car wants to travel in a nice straight line at a constant velocity. And when the car's over here, it wants to travel in a nice straight line, constant velocity. But something is making that car go around the curve to give it that curved path. What do you think the force is that's making that pull that car around in a curved shape? Well, I'll give you a hint. If we were trying to do this turning, going around this loop around here in this car, and the road were suddenly just completely ice, completely slick, what direction do you think that car would take? Of course, the car would just drive right off the side of the road, over into the embankment, and go off the road, right? So friction. Friction is the force that's going to, when you go to turn that wheel, as long as there's friction between your tires and the pavement, that car will come around the curve and form that circular path. So which way is force pulling on that car? The force of friction on this thing, on that car, is pulling right toward the center. And there over here, that force of friction is pulling toward the center. That force of friction is pulling toward the center. When the car is over here, the force is pulling toward the center. Okay? So in the first example, gravity provided that force that created that curved path. In this example, friction between the tires and the pavement is going to cause the nice curved path. Alright, now what we need to do is talk about some formulas. How to do some calculations dealing with all these different ideas. Okay? So here we have our basic circle, and every basic circle's got your center right there. And what we're going to do is we want to talk about the velocity. Okay? The velocity going around that circle. Now, we've got different kinds of velocity. We talked about velocity, we talked about speed. But when it comes to circular motion, there's like two kinds of velocity. There's a velocity that something goes around the circle in a circular motion, which is what we're not going to talk about. And then we have the instantaneous, like the velocity of this object wanting to go off at this tangent. Notice this is 90 degrees. That's a tangent right there. So we're going to put a capital T right there for the tangent velocity. When the object is over here, its velocity is at a tangent right there. So it's called the tangential velocity. When the object is over here, it has a tangential velocity. Okay? Now, the way to calculate tangential velocity is you got to think about this. Every good circle, of course, is defined by its radius. Okay? So we have a radius of our circle. Now, remember before when we calculated velocity, it was just distance or displacement divided by time. Now, the distance, this object, when it goes all the way around that circle right there, what distance has it traveled? Well, the distance around the outside of a circle, of course, you all remember, is the circumference. And what is the formula for circumference? It is 2 pi r. So 2 pi r is what we're going to use for the distance. So when an object goes around the circle one time, the distance that it's traveled is 2 pi r. So the tangential velocity, vt, is equal to the distance is 2 times pi times r divided by the time. Now, there's something special here. When the time that it takes for an object to go around a circle, or to basically what they call complete one cycle, let's say this car is going around and around and around. Every time this car, this object went around the circle, the time it takes for something that keeps on repeating its same motion over and over and over again is known as its period. Okay? As known as the period. So the period, the symbol is capital T, kind of like time, but it's capital. And that is the amount of time for one cycle. C-Y-C-L-E. Oops, sorry about that. Bad typo there. All right, that's the amount of time it takes for one complete circle, or one cycle. And that unit is going to still be in seconds. So down here in our formula, the amount of time it takes to go around 2 pi r, in other words, one time around the circle, is going to be the period. So there is my new formula right there. To calculate the tangential velocity of any object going around a circle, you're going to take 2 times pi times the radius of the circle and divide it by the amount of time it takes for it to go around the circle one time. Okay? Alright, now we need to go to a second question. The second question here about uniform circular motion is, can an object accelerate if its magnitude of velocity remains constant? Say what? What that means is that, let's say you were going around in your car here. You're driving around the circle, and on the speedometer it said 30 miles per hour. You just kept on going around and around circles at 30 miles per hour. Are you going at a constant velocity, or are you accelerating? Well, remember, velocity is a vector. Okay, it is a vector. And remember, every vector has two parts. It has a magnitude and it has a direction. If either one of those or both changes, then that means there is a change in velocity. Okay? So even though you may be going around circles at 30 miles per hour, okay, 30 miles per hour, 30 miles per hour, means your magnitude, that's not changing. But your direction, of course, look at this direction. Your velocity is going this way, it's going that way, or there's an infinite number of directions that your velocity winds up going as it makes its way all the way around the circle each time. So the direction, that is changing. And of course, if the direction is changing, then that means your velocity is changing. And if you got a change in velocity over time, that is the definition of acceleration. So that means even though a car or an object is going around a circle at a constant velocity, at 20 miles per hour, at 5 meters per second. It's going around at a constant velocity, or a constant speed. Because its direction's changing, that means it is still technically accelerating. Okay? So that answers our second question. So let's go on to go into the next two little descriptions. Did I find my paper? Where's my paper? There it is. Sorry about that. All right, so here we go. We got our one more picture. And let's say we got our object here that's going around. It's got its tangential velocity right there. And we've got this force pulling on it, right? Pulling on it this direction, right toward the center. And that happens no matter where it's at around that circle. That force is always going to pull right toward the center. That's what creates that curved path. Now, toward the center, that's what gives something its definition of centripetal. Okay? If something is said to be going around and it's centripetal, centripetal actually means, in the definition of centripetal, in the root word, it means center seeking. Okay, it means center seeking. So if anybody ever asks you, well, which direction does the force that creates a circular path, there's a force acting on it, which direction is the force pulling? Well, it's always pulling center. It's always pulling toward the center. So we're going to put a little C right there, subscript, on that force, and that's going to be centripetal force. Okay? Now, there's one other thing I want to explain to you. And for that, we're going to go back to Newton's second law. F is equal to m times A. Remember, F over here was a net force. Okay? It was a net force. And one of the things we went over is that whichever direction the net force is acting on an object, the acceleration is going to go in the exact same direction. So in other words, to put it to you really basic, let's say we go back to our box, you pull to the right with 30 newtons, you pull to the left with 20 newtons. Which way is the box going to go? And everyone's going to say, of course, it's going to go with 10 newtons left over to the right. So that would be your force that's left over. That's going to be my net force. So which way is the box going to accelerate then? It's going to also be to the right. Okay, so whichever direction the net force is pointing, your net acceleration, or the acceleration, is going to also be in the same direction. No matter which direction the net force pulls, the acceleration is going to be in the exact same direction. So that means that if you have this object going around in a circle, and we just got done saying that it's accelerating the whole time, then that means this net force, or this centripetal force right here, is also causing an acceleration of this object going around in a circle. So, and it has to point in the same direction. So that means there's, right alongside this one here, there's also a centripetal acceleration. Okay? The centripetal acceleration, that's what you feel when you go on a ride at the park and you feel that the extra G's at the bottom of the hill, or you go around a loop-de-loop and it pulls you back into your seat. That's the centripetal acceleration that you feel pulling on you. It accentuates or creates almost like an artificial gravity for you. Alright, that is the end of this part right here. Now let me show you one more thing as far as formulas go. We have two more little formulas here, and I'll be done with part one of our three-part series on circular motion. And that is, we now know how to calculate the tangential velocity, which was 2 pi r over the period. And now we can also calculate the centripetal acceleration. centripetal acceleration is going to be the tangential velocity squared divided by the radius. You take the tangential velocity and you divide it by the radius of the circle. And of course, we're going to use Newton's second law right here, and we're going to say, well, then to calculate the centripetal force, remember right here, you're just going to take the mass times the acceleration. So centripetal force is just going to be the mass times the centripetal acceleration right there, which could be just the mass times, and there's the acceleration part, tangential velocity squared over the radius. Okay, the next two videos, part 2 and part 3, we're going to go over how to calculate the tangential velocity, the centripetal acceleration, and the force, centripetal force.